The general topic is around cumulative effects. So I'm going to head off the question now and answer what I'm talking about by cumulative effects. Really what I'm talking about are cumulative impacts or changes within a watershed that would affect watershed values. And some of you may have seen this before, but I have on the left there the drivers of pressures, in the middle there watershed processes. And we'll kind of go through these and do a horrendogram, as people generally call them. I'll go through this quick. So as far as processes, I'd sort of define sort of runoff generation, hydrologic processes. We have sediment processes happening within our watersheds. We have riparian processes, and then generally, I don't deal with these very often, but there's sort of a biotic component associated with watersheds. Then we have, at least in most of Alberta, we have various things going on. And we have some of these other sort of external forces or other things that are changing our forests and our landscapes in general. And generally, you know, we think of forestry affecting hydrology. We would think of hydrology would also affect the sediment dynamics associated with where we are. In turn, we've got other things going on, and it keeps going and going. You know, these guys end up feeling the brunt of it. We've got energy companies that have roads. They use water out there. Cows like riparian areas, apparently. They also use water and impact the rangeland. We've got other things that keep going. These gentlemen here, or some ladies as well, they bring their fishing rods with them. So we get this tangled web of cumulative impacts, which generally end up impacting our watershed processes and ultimately our values, which I'll get into in a minute. Within that context, we sort of have a management framework as well. So we generally have our higher level plans. We have sub-regional plans, which then have some sort of allocation associated with them, which can change, as we just found out with the park that was announced down south with the land use framework change. There's tenure that's associated with the areas that are associated within those allocation areas. And then in this case, the forestry one, so I'll focus a little bit on the forestry one. We have sort of a policy approach to how we deal with forestry. And then there's monitoring and compliance, which feeds back through, and we have this other sort of horrendogram that we work within. I'm going to pull apart this forestry one here a little bit to explain where this concept of watershed assessments came from. So in order to cut something in Alberta, you need to have a tenure of some type. As I just sort of pointed out, there's higher level plans that feed down into that tenure, which then has a forest management plan, which has sort of a spatial representation of it. These things aren't too important, but a general development plan, final harvest plan, your operating plan, which gives you your authority to actually cut it, some ground rules, and some other legislation that might be out there. So a few years ago, when I was sort of transitioning to my secondment, there was sort of an audit done of this process by some professionals from British Columbia that really pointed out a few recommendations, but one of the main recommendations was around this concept of cumulative effects. We deal with it at the high level, but by the time we get down to the operating plan, there may have been a few changes in that time frame. So we sort of proposed in this process that we would look at developing watershed assessment procedures to sort of fit within this structure here. It's not too important. The general development plan is sort of a 5-year plan. The final harvest plan is really the plan where ribbons end up on the ground, where there's actually work being done in the field. So it made sense to review it before you actually spend investment and time and go out and lay out where blocks would be to look at what might be other values and pressures on the landscape. So there's other jurisdictions out there that have been doing similar types of assessments or analysis. So, and including a few here from Alberta that we drew upon to kind of look at how this might come together. So this, I just sort of wanted to lay as sort of the background associated with where we're working and where it was coming from. One of the first things that we were actually doing this in concurrently through what used to be the Foothills Research Institute, but is now just FRI Research. That's the way it is. It's sort of like the Prince, right? Formerly known as Prince. So we did a review of other things that were out there, and really what came out of that is we would like to base it on risk, and I'll get into this a little bit. Have 2 levels, so sort of an office base and a detailed base, and also base it on watershed processes. So if you go back to that horrendogram that I had, we can define that based on sort of sediment, riparian, hydrology, and then sort of the biotic processes that might be working within a watershed. If we're going to define it by processes, it makes sense that the hydrologic processes are different within the province depending on where you are within a hydrogeoclimatic regime. So one of the first things we did was divide it out into sort of eastern slopes and foothills as sort of the forested areas that we were initially concerned about, and having nodes of areas where we would focus research and sort of testing applied tools at the same time. So one of them being the eastern slopes, which we started first, and then the foothills. One of our first projects was really to take that review and say, what would a higher level assessment look like in an Alberta forested eastern slopes area? And the person that did this was sort of a geomorphology riparian guy, so you may notice there's not too much focus on hydrology, but a little more focus on the fish or geomorphology side, but this was sort of the framework it came from. Since then, really what we've been trying to do is come up with tools that we can use in the office, so what we've sort of been calling a level 1 sort of triage approach, in this case looking at erosion and sedimentation at Dutch Creek, which the Old Man Watershed Council was talking about earlier. Field-based ones that would augment that, so that the office space would really direct where we would have potential issues, but really focus in on field-based protocols to be able to assess what's going on in the field. In this case, Watershed Resiliency Program, where we're looking at the health of the headwater area, specifically related to the riparian areas, using a method from BC. And then the one that I want to focus on here for the majority of the time is this concept of hydrology and change in different hydrologic parameters as it relates to change in the forest condition through harvesting, through wildfire, and some of the other things that we've been working on. And again, really trying to come up with a high-level, generally GIS-based approach, but then also a field or more detailed approach where we might expect we would see potential impacts and may have to refine our risk call a little bit more. One of the things I wanted to do, and we saw this very nicely from John Pomeroy, is sort of what goes on within a forest hydrologic cycle, but I just wanted my quick cartoon one because I'm going to keep coming back to this a little bit. So in general, it rains or snows, there's interception, there's some sort of radiation, so the sun does stuff, there's evaporation, there's sublimation, which I don't know if I have on here, no I don't. There's transpiration, so trees actually use water, which then anything that sort of gets out of that may end up being surface flow, which isn't very common in forested areas, which you've heard. There's subsurface flow pathways, and there's general snowmark dynamics that go through there. And in this part of the world in particular, there's wind, and in warm, dry winds become a very important factor within our hydrologic process here in the forested areas. So if we take off the trees, what generally happens with this, so interception is down, obviously, because the canopy is removed. Transpiration, trees aren't taking up water at that point. Evaporation can sort of depends, maybe. We'll put that on that one. Wind, you know, if you're a snowpack, generally you can be exposed to wind, but again, it depends on the size opening. And then that all really has dynamics on how much water is going into the soil. And ultimately what might end up as stream flow. And we heard this from John Pomeroy. I think he said 2 times more precip, but only a third amount of flow, I think was the number that came out. So we'll kind of explore that a little bit. So at the stand scale, what this generally means, and this is a picture from when I worked in Calgary outside my window, you can see under the forest, no snow, in the opening, snow. And then things change, but you end up with more water in the soil. That's generally the concept, you know, that we would expect. At the watershed scale, it gets very complex. This becomes challenging, and we have things like desynchronization and synchronization, and we use all these terms to sort of explain what we might observe. One of the things that I wanted to do was sort of go through where we understand, how we understand what we might expect a response to be. Generally has relied on paired catchment studies. So we heard about 2 paired catchment studies today, Marmot and the Southern Rockies. The initial stuff isn't a paired catchment in the classic way because it's pretty hard to get pre-disturbance wildfire data unless you're extremely lucky. So the general paired catchment approach is you monitor 2 watersheds and then you treat one or harvest one or do whatever you want to do with one and then continue monitoring them and compare the parameters afterwards. Generally what that would look like if you look at the graph on the right is you would, in this case they're looking at the peak flows from rainfall. And I like this paper because they summarized a whole bunch of stuff that happened in North America and around the world. So I keep going back to it. And what you have on the x-axis, so on the bottom, is the basin that is the control, and what you have on the y-axis is the treated basin. And if you look closely, there's open circles, which are after the treatment, and there's closed circles, which are before treatment. And there's two regression lines, and lo and behold, in this case, you see there's an increase, and they've plotted on here the bank full discharge, which is a pretty important parameter for forest hydrologists, and you can see the increase that they've predicted associated with this technique. And this has been the classic forest hydrology technique for a century, probably, now that we're into 2015. Again, why we go back to this paper is because they summarized several of these studies across North America, and I think some overseas as well. And what they did was they plotted the area harvested on the x-axis and the change in that bank full discharge on the y-axis. And generally you can see in that 20 to 30% range, which is the classic rule of thumb for forest hydrologists, you don't expect you will see any change in this case on bank full discharge. That's generally where that rule of thumb comes from. Beyond that, it's almost a guess if you look at this. Generally what would happen is we would look at parameters associated with the watershed and the forest condition that would suggest whether or not we think the watershed is sensitive or resilient to change in forest condition. This paper, one of the main authors I just was with yesterday, is the Green and the Lila paper, where they looked at they have sort of cast doubt on this method associated with paired catchments and how we analyze it. However, one of the things that they did nicely at the top of this is they explained how you would determine whether or not you think a watershed is sensitive to change or not, depending on stand condition, the physiology of the watershed, and also the location within the watershed that you're talking about. One of the things that they're arguing is that big peaks or floods, which we would generally think of, versus small peaks or sort of the general spring freshet that we would normally see, historically, using this paired catchment study approach, forest hydrologists would assume that the smaller peaks are affected by change in forest condition, but not the floods. And they're arguing the opposite. Ironically, or not ironically, maybe thankfully, the way that we would deal with this sort of in a professional or a risk assessment approach is exactly the same. We would suggest that you limit the amount of area you harvest within a watershed within a given time so that you don't expect to see a change in these parameters. And if you go back to this one, that magic number for forest hydrologists tends to be 20 to 30%. One of the things I wanted to do with this presentation quickly, because I don't have a lot of time, is actually go back to paired catchment studies and ask the question, do we expect any change to those peak flows? Big or small or whatever was measured. Very simple grassroots stuff. Turns out that we had this project where we wanted to look around the province and figure out, do we have any of these long-term sites? I'm relatively new to Alberta, especially within this capacity. Turns out there was a lot of them in the 70s, 60s, 70s, and they all sort of ended in the 80s. Along with a lot of other kind of social things that were going on in Alberta, would be my guess, in addition to the Forest Service moving off. Some of them we have, and because they were run by governments, the data are available to government people and others. Because I'm government, I can sneak in there and get them. Some of these newer ones, so F would be Southern Rockies, E I think is actually Sibbald Creek, so Sherry Westbrook stuff. They're newer, and they're generally developed in partnership with academics. So academics generally own the data associated with them. So the ones I'm going to run through are the ones that were in the 70s and 80s, and really ask the question, what were they doing and what did we see as a response? This general project, I just sort of put really what we're up to associated with it. It really wasn't intended for use for this purposes. It was more just collecting the data and making it available to those that may want to use it. So I thought we'd start with Marmot and see if you guys can remember what happened. So at Marmot Creek, the level of harvest, John pointed out, I wrote the 23 because that was the only one I could find in the literature I had. So Cabin Creek, 23% of the area was harvested. A good portion of it is alpine. So the area of the forested harvested is like the forested area that's harvested is higher, but a good portion of it is alpine, and that's where the majority of the water is coming. So If we look at the schematic that Green and Alila said, this is one of these areas that we would expect to be not sensitive to change. And lo and behold, if you read the paper that John had sort of talked about a bit with the resiliency, as you plot up the Cabin Creek stuff, there's actually a decline, and there's all sorts of reasons we can suggest why this might happen. But after you harvest, there's a measured decline associated with it. I'm not using the data that John has recently, so in the 2000s, this is just the data that I can access from the government sites. The catchment where they tried to produce more water, the same kind of concept, but this isn't statistically significant. And what we have here is the same as what I showed before, blue being before and red being after. And really no difference associated with them. Here's another one that we pulled out. This is actually, if you look at the top right, this is Streeter Creek. So Streeter Creek was a rangeland improvement one that they did. Essentially what they did here is actually not really do forest management, but they actually tried to remove the forest in a way that would capture snow, but used it as a snow fence approach. So they tried to make openings that were against the prevailing wind, with the intent being that they would catch snow and then also not be impacted by the winds that would sublimate the snow. In this case, there is a change. These are tiny, tiny small springs. They intended to have larger ones, but they ended up monitoring really small springs. 70s, 80s, another sort of general issue with these types of studies, non-stationarity, or the fact that before and after are not necessarily the same. There was a PDO shift right in the middle of it. So there was sort of wet years before and dry years after. So often a lot of the dry years follow up afterwards. This from a forest hydrology perspective, those two were fairly tame. 23%, 17% area impacted. This one is up, this is Tri-Creek. So this was, what is the impact of buffers and no buffers on fish? And in this case, there's 3 streams. One of them, they logged 63% of it over a series of years. One of it, they logged 50%, and they took all the buffers that they could. So there was no riparian buffer associated with this one. And from a forest hydrology perspective, we're starting to get to the point where we'd be excited. There's no alpine area, it's flat, it's all facing a particular direction. We're not likely getting a lot of those Chinook winds in this part of the world, so we're going to get a significant snowpack. When we plot these ones, we see the same thing. And this is soon to be the bane of a PhD student's existence as to why we don't see a response when we harvest 63% of it. And again, 50% of it with no buffers. This is we'd expect to see a change. If we go a little further north, this was an interesting one. This one is Spring Creek. So this is Valley View is right off to the right-hand corner of this. This was set up to be a land use change experiment. So what they really wanted to do, see if this will work. There's 2 watersheds here, which are more wetland than watershed. And then off to the left of the screen, off to the west, is white zone, and there's development changing through there. So they had catchments that they were expecting would be converted from forest to agriculture land and be able to monitor that. It was actually shut down before that conversion actually happened, so that didn't happen. This area is under tenure from a forest company that harvests the deciduous, not the conifers, and they went in and they harvested about 23% of the area of one of them in a paired catchment study in the 90s. So they ran in the 70s, they got their pre-disturbance data, they shut everything down, and then they restarted it in the 90s with the Canadian Forest Service and a few others to look at what happened. In this case, we do see what we'd expect. We'd see this increase after. One other one, and this is really what started the whole thing. So this is, again, I mentioned the fire. We can't look at pre-disturbance within fire, so we have to make up data. In this case, we're using modeling techniques to try and look at what was the impact of that fire. And as Aldous pointed out, and there were some good questions associated with what happened to the hydrology. In this case, not only do we have a change in the vegetation, which it's all gone, it's all been burned other than the stems, the soils themselves have actually changed. And we would expect, due to hydrophobicity, which apparently gives people problems when you're trying to treat the water, it also gives you problems when you're trying to look at runoff issues. We would expect we'd see big changes. And in fact, we didn't. And this actually really started the whole thing. So if we just sort of summarize this quickly in 1 minute or less, really what we have here is sort of a series of watersheds that tend to plot in this area where we don't see much change. And then we have another series of watersheds where we're seeing the expected change that we'd expect. There is a change happening. You can think about all this is just sort of preliminary data and preliminary ideas of why these are different. One of the things I wanted to run through is perhaps this idea, expand on this idea that I'm glad John brought up at the beginning of soils and what's going on, not necessarily with the soils, but with this concept of this runoff generation. So we know there's more water hitting the surface, what's going on. Our historical idea of thinking is the water would go down, build up a water table, which would have high hydraulic conductivity, which just means the water is going to move fast and would move quickly towards the stream. And essentially this is represented by a leaky bucket with bigger holes as you get to the top. More water you put in, the quicker it's going to come out, which creates a very fast response. Deeper soils, other things are going to have other issues. As we move into this concept, Aldous pointed out the fact that we have a glaciated landscape over top of sedimentary rocks, and that we have extra fine soils. So water doesn't actually, or not extra fine, I shouldn't use that qualifier, but we have fine soils overlaying sedimentary rocks, so porous rocks. So what happens if what's actually happening is not only this is water not necessarily moving downstream, but perhaps moving vertically into the bedrock, because the fine soils, even if we do build a water table, have low hydraulic conductivity, which is going to resist moving down the hill, but they are sitting on top of very porous sedimentary rocks. Just a hypothesis. So this has implications for buffering, for the amount of area that may contribute to the stream. So the fact that we have twice as much water, but maybe only a certain percentage of the watersheds contributing to the stream. How do we deal with this? Well, we have another student looking at what are the sources of water at sort of high, medium, and low levels of runoff. One of the last things I wanted to touch on quickly is the use of models and some of the techniques that we're trying to use. In this I won't talk about too much, but because I don't have the time, but we've been able to identify different zones within the watershed and trace where the water is coming from within the hydrograph. So if you look at the bottom one, it really shows the different zones which is happening. And then if we are to plot that at a figure, it'll actually tell us where most of our water is coming from. So in this case, for sort of the peaks that we'd measured, we'd expect 75% of the water for that peak is actually coming from that higher elevation, which gives us sort of a map of what we already know and corroborate what we know as forest hydrologists. So it's the last slide I really wanted to follow up with. It's just this sort of reminder that this is one of the concepts that we're working in within this sort of triad of different approaches of watershed processes, where we want to make sure we have office-based and field-based assessment tools, but that they're also based on science that's feeding into those that are based on local areas. And just as a thank you note, I just sort of wanted to thank everybody that was funded, but also the people that actually go out in the field and collect data that we can then use to do these types of things are very important.